Good evening, everyone. I'm Shikha Agarwal. I'm a research scholar at IIT Madras, and this is our 12th day session on the topic of designing steel structure. So, in this 12th week, you might have studied about the design of gantry girders. We have already seen what are the gantry girders and what are the different design steps for gantry girders. In this week, you have might have solved one example question for the design of these type of gantry girders. Secondly, you might have studied about different type of base plates. Or should I say column bases, steel column bases. So mainly we have two type of column bases, slab base and gusseted base. So in slab base, what is a slab base and how we can design this type of slab base? And secondly, what like eccentrically loaded base plate? And lastly, gusset plate. What is a gusset plate and how we can design this type of column bases? So a little overview about the gantry girders. So these gantry girders are the laterally unsupported beams which will carry heavy load from one place to another, and they are normally installed in the many factories and industries. So if we see this figure, uh, these girders which are going from one point to another are called gantry girders, and above these gantry girders we have rails, and above the rails we have our crane bridge, and over the crane bridge we have our trolley or cab. So this is our gantry girders, these two lines, and then we have our crane over it and trolley over the crane. So this is a complete assembly of our gantry girder, and these are the different components of our gantry girder: crane, then we have rails, gantry girder, and then we have columns which are supporting the gantry girders. Okay. So this all we have already studied in last week. Just for the design purpose, we will go through it again. So in for the design of gantry girder, three things have to be for the maximum load effect. We are considering three cases. Firstly, what should be the position of our crane hook for the maximum vertical load on gantry girders? So if these are our gantry girder and this is our crane, and then we have a trolley, and trolley have a hook. So what should be the position of this trolley so that we have maximum vertical load over our gantry girders? So it should be placed as close to gantry girder as possible, and this will be the formula for the reaction on our gantry girder. So if I are to consider the maximum loading on the gantry girder, we will assume that our crane hook is placed as close as possible to our gantry girders. Secondly, what should be the position of crane wheels for the maximum effect on gantry girders? So, if we see these are the gantry girders, and this is our crane. So, if we look from this point of view, then this will be our gantry girder, and above this will be our crane, which will have two wheels, right? So that's why we are taking 2 point loads. So this is our complete span of one gantry girder. This is our crane wheels. So this should be the position of our crane wheel. We calculate that CG of our gantry girder and CG of this crane girder. This crane have a equal distance. Should be equidistant at A by 4 like this thing, and this will give the maximum effect on the gantry girders. Next and last thing is the what should be the position of the wheels for the maximum shear on gantry girder. So this is the case for the maximum loading, bending moment especially. And in case of shear, maximum shear, we assume that one wheel of our crane is lying on the end of our gantry girder. So this is the different position of cranes and trolleys for the maximum effect on our gantry girders. Next is the what are the different design procedure of our gantry girder. So first thing, we are calculating the maximum wheel load. Then we will calculate the maximum vertical load on our gantry girder using the first case one, which we have seen now. And then we will position our crane in such a way that we are getting maximum moment and maximum shear on our gantry girder. So for maximum moment, we are calculating that CG point of gantry girder and CG point of our wheel load should have a equidistance. And then for the maximum shear, we are telling one of our wheels should be on the end of our gantry girder. So after positioning of this thing, we are adding the impact load for to our gantry girder. So it will depend on the what type of gantry girder is this that is already given in our IS code. That if it's like different type of girders, and what is the additional impact load we are adding. It can be 10% of total load, 25%, that kind of thing. So next step is we are calculating maximum shear force due to the vertical load. So after positioning our gantry girder in a position, we are calculating maximum loads. Then after calculating maximum load, we will calculate the maximum shear force. And then after calculating shear force, we are calculating the lateral forces on the girder. So when we get maximum movement, maximum shear force, then we calculate the lateral forces on the girders. After calculating the lateral forces, we are getting the Z value. Sorry, section modulus. We will calculate the section modulus ZPP. So this is the formula of ZPP, ME upon Fy. Maximum movement we have already calculated. Fy will be given to us. So after calculating the section modulus, we will select a I section. Normally I section we will select for a gentle girders. We will select a I section based on our ZP value. Okay. So after getting the section, when we have the section, we are after getting trial section, we will have some condition that our section should follow. That is, ZP trial should be equal to KZP, where K can vary from 1.3 to 1.60. And after calculating these things, we have to check that our depth of gantry girder is about 1/12 of span, and the width of flange should be about 140 to 138 of the span. So these are the checks we will apply. After getting this check, we will choose a suitable section, and then different properties like IZZ, IYY, ZD, ZY, ZP, ZZ. All these properties will be already given to us for that particular section in our steel table or SP course. So based on our D upon TF and D upon TW ratio, we will classify our section as plastic, compact or semi-compact. So when after this thing, we will check our section for moment capacity. So this will be the formula of check for moment capacity. After checking for the moment capacity, we will check it for the local capacity. That this is the formula for the local capacity. After that, we will apply different check like check against shear, check against local buckling. So all these formulas we have already studied in all the weeks, and it's given in IS code also. So we will check it for against shear, local buckling. Then for bearing stiffness, and then deflection, we have the different formulas in IS 800 for the check for deflection. And lastly, we will check it for the fatigue strength. So in last week, we have already studied the different formulas for the fatigue strength check. So we will apply that check. So this is all about the gantry girder and its design. And one question has already been solved in the lectures already for the gantry girder. So you can look upon that, and we are following the same procedure for that example. Next thing we studied in this week is the column bases. So column bases are normally a plate or plate and anchorage assembly, which are provided at the base of our column, which will transfer the load from column to foundation. So they are column bases usually supported by a concrete slab or substructure, or we can say the foundation. So if we look at this diagram, this is our column, and this is a base plate we are providing, which is we are normally calling as column bases. So the main function of the column base is to transfer the loads from the column to the foundation. So other advantage of column base is that it stores the load in the wider area, so that the intensity of bearing pressure on the foundation block is within the bearing strength. So instead of directly transferring load from column to foundation, we are giving a wider area surface to the foundation, which will help in decreasing the stress into the foundation system. Okay. So we have mainly two type of column bases. One is slab base and second is gusset base. So in slab base, we are normally providing a simple slab surface between column and foundation. So it can be riveted, it can be riveted, or it can be bolted, or it can be welded onto the foundation surface. Next thing is gusset plate. So we are providing uh, with the plate, we are providing some gusset on the sides of our column. So this is the usual shape of our gusset plate, and from the top view, it looks like two singular plates like this. So if this is our this is our normal, what we say, this is our column. So this will be two gusset plate we are providing, and below those gusset plate we are providing a base plate. So these are the two type of column bases we have. So first thing is the slab base. So this is how exactly a slab base look like. So in the slab base is provided when the column carrying the smaller load. Generally, only axial load. If only axial loads are there, then we are providing a slab base. So it consists of a thick steel base plate placed over the concrete base and connected through the bolts or welding. So if this is our foundation, above foundation we are providing a simple steel plates which is connected to two bolts, and it is connected to our column section through different plates. So this is a slab base. It can be welded to the section or can be joined to the column through cleat angle. So this L type of section you can see, these are called as cleat angles. So they are joined through our column either by welding or through some cleat angles, which are usually bolted to it. So slab based are mostly suitable and economically for the lightly loaded columns, and the when we go for the design of our slab base, it requires consideration of bearing pressure on the supporting material and bending of the plate. Okay. So if we see the connection of our column and end to the base plate, we are telling it is connected through cleat web or it is connected through welding. So these are the two type of connection we are providing. So if we are providing bolts, then it is uh, we are generally providing 2 to 4 bolts, and when base is subjected to the only axial compressive load, 2 bolts are enough. But if it is subjected to loads as well as movements, then we will design our bolts for movement also. The number of bolts will increase. And when it is welded, when the column and then base plate are not machined properly, then the column should be connected by welding. If they are machined properly and perfect bearing is ensured, then axial load is assumed to be transferred directly, and the welding is designed for the movement only if the gusset plate is not required, or cleat angle may be omitted if the base plate is shop welded to the column. So what it is telling, in case the welding is provided properly, we don't need cleat angles. We can directly just do the welding of our columns to our base plate. Okay. So in terms of our slab base, whatever different theoretical condition we are assuming, firstly is that maximum bending moments occurs at the edge of column. So instead of considering that bending moment is occurring in the center of our column, we are assuming maximum bending moment is acting at the edge of column for the worst case possible. And as the slab base tends to bend simultaneously about its two principal axes, the stress caused by bending about one axis is influenced by the stress due to bending about the other axis. So these are the formula which we are taking in the consideration of our slab base. So let us consider that uh, we will consider one unit length of our strip of a slab, and so maximum bending moment will be given as WL square by 2. So this is for our UDL, and W will be the intensity of bearing pressure. So we are assuming our bearing pressure is act as an UDL, and we are taking it as a simply supported beam. So our maximum bending moment will be given as WL square by 2. It is given as the from the contour below the basement. And along y axis, like along axis, we are taking as a UDL, and along y axis, it is given by W into D square by 2. Okay. If this is A is to B, Along x-axis, it is given by WA square by 2. Along the v-axis, the WB square by 2. So assuming Poisson ratio as 0.3, effective moment along x-axis is given by WA square by 2 minus mu WB square by 2. And similarly, the moment capacity of plate is given by MP is equal to 1.2 FYZD. This is the same formula we have been using for our normal previous design, beams design. Same thing we are using here, where Z is given by, is the section modulus, is given by T square by 6. Since this is a plate, base plate is like a rectangular section. So ZD can be I by 2. That is T square by I by 2 means BD cube by 12 we have now. And ZD will be given by this divided by D by 2. So it will give T square by 6. T is the thickness of base plate. So using this formula here, we are getting MP is equal to 1.2 Fy into sorry, T square by 6. Okay. Next thing is using these two equation, we can get that MP is equal to W by 2 A square minus 0.3 B square. And applying partial safety factor divided by gamma m naught, we are getting that T is given as thickness of our plate will be given by this formula, where thickness is under root 2.5 W. W is the load intensity or bearing pressure into A square minus 0.3 B square into gamma m naught upon Fy. Okay. Next is the what are the different design steps of slab base. So first thing, we are assuming suitable grade of concrete. So from that grade of concrete, we will calculate the bearing strength of our concrete using the formula 0.45 FCK. So after calculating the bearing pressure or bearing strength, we will calculate the area of the slab plate required, which will given as load upon stress. Area is equal to load upon stress. So when we get the area, we will assume some size of our plate. A is equal to B into D or B into T in our case, B into D. Sorry, in our case it is A into B. So A into B, we'll assume some A into B, and for economy purpose, we will assume that the projection of A and B are equal. After that, after calculating the area, we will again go back and calculating our bearing pressure W, which is given by B upon area of base plate provided. So this is the base area required, and this is the area calculated. After this, we will calculate the minimum thickness. So this is the formula we have calculated previously. So we'll calculate the minimum thickness, and the thickness of our base plate should always be greater than the thickness of the flange of our column. Okay. So after providing thickness, we will provide 2 or 4 bolts, and then check if in case we are providing welding, we will check for the welding length connecting the base plate with the column. So this is the main design of our simple design of our slab base. Second thing is, in case our column is not loaded into the not loaded centrically. So in case our column is provided at some corner, like in this case, it is not provided in the center. In case it is provided at some one corner or it is centrically loaded, in that case, the design step will be little bit different. So in this case, what we are telling, we are calculate the moment, and moment is given by load into eccentricity. M is equal to P into A. And after due to axial load P, the pressure distribution is uniform and the stress diagram will be not rectangular only. So we will calculate the direct stress using the formula P upon area, where P area is length into width of our base plate, or we can say A into B also. So due to this bending moment, due to eccentricity, the bending stress is developed is given by M upon I into Y. I will be similar BL cube upon 12, and Y will be given by L by 2. So our bending moment is given by 6PE upon BL square. So the combined stress due to axial load and bending moment is given by P upon area, P upon LB plus 6P upon BL square. Okay. So solving it, combined stress due to load and bending moment is given by P upon LB into 1 plus minus 6C upon L, where E is our eccentricity. So depending on our eccentricity and length of the base plate, three cases are possible. Firstly, when there is no tension. When there is no tension, this value 1 minus 6E upon L will be given, will be equal to 0, and in that case our E is equal to L by 6. Second case is when tension developed is small. If tension developed is small, then our eccentricity is given from L upon 6 to L upon 3. And when the tension developed is a big or quite substantial, then our E value will be greater than L by 3. Okay. So in all three different cases, what is the design steps, or what are the different stresses, combined stress we can assume is, first case when there is no tension, then we are telling our E should be less than L by 6. Case 1, E is equal to L by 6 it is written, but let us assume it is E less than or equal to L by 6. Can be equal to. So in this case, the entire base plate is under compression. So we are telling there is no tension. So the maximum pressure from the concrete must not exceed the bearing strength of concrete, which is given as 0.45 FCK. So this was the formula of combined stresses. We are putting E is equal to L by 6. If we put E is equal to L by 6, this will cancel out. So F will become is equal to 2P upon LB or 0. So in case of 1, it will be 2B. In case of plus, it will be 2P upon LB. In case of minus, it will be 0. So in that case, our combined stress should be less than equal to 0.45 FCK. So using that equation, we can get the width of our B of our base plate as 2P upon 0.5 per L upon FCK. So the thickness of plate, after the calculating B, the thickness of plate is computed by equating the moment capacity of base plate to the moment at the critical section, which is assumed to be at the outer edge of the column flange. So next case is in case when tension is very low. In that case, we are assuming our E is varying from L by 6 to L by 3. In that case, first thing is most part of the base plate is under compression, where very less tension is there. So in that case, we are telling E is varying from L by 3 to L by 6 to L by 3. So we will calculate the length of plate under compression, which is given by X by 3 plus E, which is equal to L by 2. So from there, the length of plate under compression X is given by 3 into L by 2 minus E. Next is we will calculate the width of our base plate. So compressive force in concrete is given as area of stress triangle. If this is our base plate and this is our column, so this stress triangle will be formed under the base plate. So compressive force is given as area of stress triangle into width. So area of stress triangle is given by 0.45 FCK into X by 2, and width of our base plate is B. So using this formula, we can get the width of our base plate, which is given by 2P upon 0.45 FCK into 3 into L by 2 minus E. Last thing is again thickness. How we will calculate the thickness of base plate? We will calculate by equating moment capacity to the moment at critical section. Okay, same formula is there. So last case is when our E is greater than L by 3. In this case, we are telling we have sufficient tension in our base plate, and in that case, it is uh, it is taken by the tension is taken by anchor bolts. So in that case, we are assuming like first we will calculate the size of our plate space L into B, the same formula which we have been using before. And for the equilibrium of the forces, we will assume that our P, our axial force, is equal to 0.45 FCK into B minus FB. FB is our tensile force in the bolts, and the moment is calculated as 0.45 FCK B into L by 2 minus X by 2. this is the moment formula generally we are using for eccentricity minus due to moment due to R tensile force, which is given by FB into A. So A is the distance of poles from the CG of the column. So this value of X, it can be determined from this equation. If we rearrange this equation, our X value can be calculated as this formula L by 2 plus A into full bracket L by 2 plus A square minus 2 into M plus B upon 0.45 FCKB whole का under root. Okay. So after calculating this X value, the maximum moment is calculated at the critical sections. So this was the moment at the equilibrium section, and this is at the critical section. So we will calculate the moment at critical section where C2 is given by the outstand of base plate from the column flange. So after calculating the moment, we will calculate the thickness of our base plate. So again, we are using the same formula, equating moment capacity of base plate to the critical section moment, and from this we can calculate the thickness of our base plate. Next thing is we are calculating the design tensile forces in the boards. So this is this formula we are using 0.45 FCKB minus FB, where design tensile force rearranging it, we can get the design tensile forces in the boards. So in such cases, welded connection is designed to join the column section with the base of for the maximum tension in the column flange due to the applied moment. So this is all about the various design consideration in case of our eccentrically loaded base plate. Otherwise, complete design will be almost similar to what we have seen for the design of a slab plate. Last thing is the gusset bases. So if along with our base plate, yeah, along with the base plate, if we are providing a gusset plate along the column, it look like this. It will have a bigger area at the bottom and a smaller area at the top, so it will distribute our stresses more. So why we are providing this gusset base? It is normally provided when we have very high loads. So it is connecting to the base plate through gusset plate. So this is our gusset plate, and these are used for the columns carrying very heavy loads, including movements. So the load is transferred to the base partly through bearing and partly through the gusset plate. And the gusset and stiffness bear the base slab against bending, and therefore a thinner base can be provided. So since we are providing our gusset plate also along with our base plate, so the base plate can be thinner as compared to the slab base, since it is like less load have to be transferred. So in case of our gusset plates, what are the different theoretical consideration we are taking for the design? Firstly, the critical section is assumed to lie at the root of our fillet of the angle section for bolted connection, as the load from the flanges of the column is transferred to the base plate through the gusset material. Okay. Second thing is that for the unit width of plate, bending moment at critical section is given by same formula WC square by 2, where the C is the portion of the base plate acting as the cantilever. So extra part like this cantilever part will give us the C. So next thing is the design bending strength at the critical section is given by 1.2 FyZd upon gamma m naught. So ZD again, since it is a rectangular plate, will be given by T square by 6. So using that formula, our design bending strength is given by 0.2 Fy T square upon gamma m naught. So what are the different design steps in case of a gusset plate? Firstly, same way as the slab plate, we are assuming the grade of concrete. From grade of concrete, we are calculating the bearing strength of concrete, that is W, which is given by 0.45 FCK. Again, from our stress, we will calculate our area of slab. Area is given by load upon stress. So after calculating the area, we will calculate the size of our plate. So in case of gusset plate, what we are telling that a gusset plate should not be less than 60 mm thickness for bolted gusset base, The gusset or cleat angle is chosen so as to accommodate two rows of bolts in the vertical leg and one row of bolt in the horizontal leg. Therefore, an unequal angle section is normally provided. So, if this type of cleat angle is provided, so we are telling that we should have two rows of bolts in the vertical section. It should be two rows of bolts, and in the horizontal section, one row of bolt should be provided. So because of this, we are providing unequal angle section in our gusset base. Next thing is that the thickness of cleat angle is kept approximately equal to the thickness of our gusset plate. So, and next consideration is the length of our gusset material is normally kept equal to the length of the base plate parallel to the flange of the column. So for the welded gusset plate, cleat angles will not be required, as we have seen in the design consideration itself, that when we are providing welded gusset plate, our cleat angles are not required. So next step in design is so we have calculated the area, and from area we have calculated the size of our base gusset plate. After calculating the size of our gusset plate, we are calculating the uh, base length of our base plate. Okay, for size is equal to length into width of our gusset plate. Then we are calculating the dimension of the base plate. So for bolted connection, our length of base plate is given as depth of section plus 2 times thickness of gusset plate plus leg length of angle plus overhang. So this is the formula we are using for bolted connection, and in case of welded connection, our length of base plate is given by depth of section plus 2 times thickness of gusset plate plus overhang. So in this case, we are not providing any cleat angle, so this leg length will be removed. And last thing is the dimension of base plate parallel to the flanges given by area upon L of our gusset plate. So after calculating our dimension for gusset base and dimension for the base plate, we will calculate the intensity of pressure similar as we have calculated for the slab base. It is given by load upon area of the base plate provided. After calculating the intensity of pressure, we are calculating the thickness of base plate, and same we will use 2 to 4 bolts in number, and normally 20 diameter are provided in case of our gusset plates. So this is all an overview of what you might have studied in week 12. Next, we will go to the problem and solution section. Before that, if anybody have any problem, you can ask. Okay. So we'll go to some problems for this week, which will help you solve your assignment for week 12. First question is, gusset base is a type of slab base, column base, both A and B, or none of the above? So this is our diagram for the gusset base. So what do you think we can be the answer? We have already seen that our gusset base is a type of column base. Even slab base is a one of the type of column base. The column base will have two types, gusset and slab base. So answer is column base. Next question is, a column section carries a factored axial compressive load of 960 kilonewton and a factor bending moment of 120 kilonewton. If a square base plate having 500 size is provided, then the base plate will experience compression throughout. Part of the plate will be in compression with substantial tension. Most part is under compression, or none of the above. Let us try to solve it. In these kind of cases, what we have to calculate? We have to calculate our eccentricity. So what is given to us? Bending moment and axial load. So using this formula, E is equal to m upon P, we can calculate our eccentricity, which is 125 mm. Now we have the length of our base plate. So from the length of base plate, E upon L will be given to us 1 upon 4. That means E is in between L upon 6 and L upon 3. So we have seen three cases where one is E is more than L upon 6, E is between L upon 6 and L upon 3, and third is E is more than L upon 3. So in this case, this is the case 2 where E is between L upon 6 and L upon 3. So the answer will be most part of the base plate will be under compression. Okay, and with very less tension in the plate. Okay, so the next question is, in case of an axially loaded column machined for full bearing, the fastening connecting the column to the base plate and gusseted base are designed for 100% of the column load, 50% of the column weight, 25% of the column load, or erection load only. So this you might have in one of the example which sir have showed in case of gusset plate. This was the statement given that if column end and gusset materials have complete bearing or full bearing, 50% of the load will be passed directly and the 50% will pass through connection. Okay. So the answer is B, 50% of the column loads. So the next question is, a column carries a factored axial compressive load P of 1400 kilonewton. Calculate the area of the slab base required in the designing of the gusset base if it is made up of M25 grade of concrete. Take 2 minutes and try to calculate it. So from the load, we can calculate the area of our slab base. It is given by P upon 0.55 FCK. So it is already given M25 grade of concrete. So area of slab is given by load 1400 kilonewton converted into Newton divided by 0.45 FCK 25. So area will be 1244.44 centimeters square. Okay. So the next question is, consider the following statements about the function of column base. Number one, column base provides a stiffer medium to link the column with foundation bed. Column base increases the bearing pressure even higher than bearing strength of the foundation base. Column base transfers the load from column to its foundation bed. Choose the correct option. So if we see one point, column base provides a stiffer medium to link the column with the foundation bed. So normally our foundation bed is concrete and our column, if we are seeing in steel design, our column is made of steel. So to increase, to reduce the stresses into a foundation, we are providing a column base, which will increase the area and reduces the stresses provided to the column. So yes, it provides a stiffer medium to link the column with foundation bed. So this is the correct option. Second thing they are telling is it increases the bearing pressure even higher than the bearing strength of the foundation bed. So this is wrong. Normally we are telling our base plate actually decreases the bearing pressure. It decreases the bearing pressure onto the foundation bed. So this is the wrong option. Third is the column base transfer the load from column to its foundation bed. So this is the correct option. This is the main usage of our column bases. So the correct option will be first and third. B. Right? So going to the next question. In case of a column connected to the base plate through gusset plate, The loads are transferred from column to base plate, partially through friction and partially through gusset plate, partially through bending and partially through gusset plate, partially through bearing and partially through gusset plate, partially through shear and partially through gusset plate. So this we have seen in the theory itself. When we are providing gusset plate, the load are transferred through partially through the bearings and partially through the gusset plate. So next numerical is a bolted gusset plate is used to transfer an axial load of magnitude 1500 kilonewton from a column made of ISHB 350 at 72.4 kg per meter, where depth of section is given as 350 mm and flange width is given by 250 mm. If the thickness of gusset plate is 14 mm, length of pleat angle is 75 mm, and overhang is 60 mm, then find the length of gusset plate parallel to the web of column section. So first thing is, in we have two direct formula in case of eccentricity, that length of gusset plate parallel to web of section is given by, parallel means in x direction. So in x direction we told it is depth of section plus 2 times thickness of plate plus length of pleat angle plus overhang. Right? You remember this we read about in one slide, that in case of bolts we are using this formula, and in case of welding this thing will be removed. So this L is given by depth of section is 350 mm plus 2 times thickness of gusset plate. Thickness of gusset plate is 14 mm plus length of pleat angle. Length of pleat angle 75 mm plus overhang. Overhang is 60 mm. Using this formula, our length of gusset plate is given as 650 mm. Okay. We'll go to the next question. A, a slab base is used for the column to transfer a vector load of 1200 kilonewton, and this load causes intensity of pressure 7.4 megapascal on the base plate from concrete pedestal. If larger and smaller projections are 75 mm and 50 mm respectively of the slab base beyond the rectangular circumscribing the column, find the minimum thickness of the base plate. So the flange thickness of the compression member is given as 14.1 mm and grade of steel is 410. So how to solve this type of question? Firstly, we have given the pressure intensity W as 7.4 megapascal, and for F 410 grade of steel, Fi is given by 250 megapascal. Now, we have two projections of the slab base, larger A 75 mm, smaller B 50 mm. And then we can calculate the thickness of our base plate. Thickness of base plate is given by this formula. We have already seen, like equating those things, we calculate the thickness of base plate. It is 2.5 W into A square minus 0.3 B square into gamma m divided by F5. Putting all these things into the formula, we will get the thickness of base plate as 19.92 mm. So this thickness of base plate should always be greater than thickness of flange. So our thickness of flange is 14.1 mm. If it is greater, then our section design is okay. So the thickness of base plate is given as 19.9, which is closer to 20. Okay. To the next question. A base plate of size 500 mm into 400 mm into 12 mm is used to transfer the vector load of magnitude 1200 kilonewton coming from the column. If the load acts as an eccentricity of 60 mm, along the longest dimension of the plate, find the extreme stresses in the plate. So in this case, first we will get the uh, what all is given to us. Length of base plate 500 mm, width 400 mm, and eccentricity 60 mm, and the effector load is given as 1200 kilonewton. So from firstly, extreme stresses are given by, this was the formula we have seen previously, F is equal to P upon LB, 1 plus minus 6C upon L. So all of these things are already given to us. P is equal to 1000 kilonewton, L 500 mm, B 400, E 60 mm, and L is 500 mm. So solving this formula, we can get our F is 1.68 MPa and 10.32 MPa. D option. Okay. So the last question for today's session is, a 7.5-meter long gantry girder experiences total load of 350 kilonewton from the crane girder. This includes the crane girder capacity and self weight of the crane girder, trolley, hook, and wheel assembly through two identical wheels spaced at 3 meters. If the self weight of gantry girder is 1.75 kilonewton per meter and the crane is eccentrically operated, find the design vertical shear on the gantry girder. Impact factor will be taken as 25% and partial safety factor as 20%. You can take 5 minutes and try to solve the question. Solve the question. First thing, what is given to us, that the total load of crane girder is, the total load of crane girder will be distributed equally among two wheels. So if we see for the maximum shear, we are telling our one wheel of gantry girder should be kept at one corner of our, one wheel of our crane should be kept at the corner of our gantry girder. So two wheels at equidistant at 3 meters, and the load on the crane is 350 kilonewton, which will be equally distributed among two wheels, 175 and 175. And then what is given to us? Total length of our gantry girder 7.5 meter and UDL of 1.75 kilonewton per meter. Okay, I hope this diagram is clear to you. Then what we have to calculate? We have to calculate the design vertical shear on the gantry girder. So solving this beam equation, we will calculate maximum shear due to V loading. We will calculate the reaction at RA and reaction at RA. So RA will be given as 175 plus this thing 7.5 minus 3, 7.5 minus 3. We will use the moment equation, like calculating moment at RB. So RA minus 175 into L plus 7.5 minus 3 into divided by 7.5 into 175. So this will give us reaction at A. RA value will be 280 kilonewton. Next thing is, so the design vertical shear force due to applied loading, then we will multiply it by the impact factor and factor of safety. Multiplying by these two values, we are getting the vertical shear force as 595 kilonewton. Okay. So next thing is due to the self weight. So that we calculated due to the crane girder. Now we will calculate the shear force due to self weight. So shear force due to self weight is given by 1.7 of gamma into W into L by 2. So L is 7.5, using this formula, we are getting design shear force as 11.156. So total shear force will be due to crane plus due to self weight, which is given as 595 plus 11.16 is or equal to 607 kilonewton. Okay. So that's all for today. And that was the complete syllabus of design of steel structure. In case you guys have any problem, you can contact me on my mail IDs. These are my mail IDs. Thank you. If you have any doubt, you can ask me.
Ma'am, can you share these notes?
Yeah, I think everything I have already uploaded on the Google Drive link. You have that link with you?
Ah, yes, ma'am.
Yeah, today's also I will upload there. Yeah.
Okay, ma'am.